Our next talk is going to be by Cheng from Shanghai Jiaotong University. He's going to be telling us about compositional compiler verification.
Thank you. Thank you for the introduction. Hello, everyone. My name is Zhang. Today, I will present our work, Denotation-based Compositional Compiler Verification. CompCert is one of the most influential verified compilers. Its correctness proof is based on small-step semantics and simulation theory. Intuitively, simulation means that each target step is matched by 0 or more source steps producing the same event and reaching related states. This is powerful, but the proof structure is not always easy to reuse. Here is a small example. Suppose f and g are pure computations. They do not have I/O events, and they do not change the input variable x. If f is compiled to g, then in another context, the target program can compute y first and move print operations later. However, a simulation proof for fragment f to g is hard to reuse directly for the natural transformation s to t. The reason is that observable events, such as print, must be matched step by step in the simulation proof. If we look at simple text-to denotational semantics, it is clearly compositional. Here, the semantics of a statement is defined as a binary relation between initial and final states. For some simple program transformations, their correctness can be defined by set inclusion. Then the correctness for sequential composition can be proved compositionally. However, programming languages such as C have much richer language features and more possible behaviors. Moreover, compilers often change the memory layout and the representation of program states. So set inclusion is no longer enough. We need more general refinement relations to relate source and target states. Traditional denotational approaches address parts of this problem. For example, power domain theory provides standard ways to model non-determinism and non-termination. They usually rely on a single global order on behaviors so that fixed points can be constructed to define the semantics of the recursion. But to keep the order simple, divergence is often handled in an absorbing way. In a partial correctness view, divergence is absorbed by terminating behaviors. In a total correctness view, divergence instead absorbs terminating behaviors. Neither treatment is suitable for compiler correctness, since divergent behavior must be preserved precisely together with its observable events. On the other hand, once we disallow this kind of absorption, it becomes hard to find a natural global order that handles all these language features. This leads to our key question. Once we consider all these features, can we keep denotational semantics precise with simple order structures while still having algebraic correctness proof? Our answer is yes. I will show. We begin with the semantics of statements. Consider a small language with non-deterministic choices and while loops. In this setting, the execution of a statement C may terminate normally, abort, or diverge. We describe semantics using 3 separate behavior sets. The normal behavior is a binary relation between initial and final states. The error behavior is a set of initial states from which C may abort, and the divergent behavior is a set of initial states from which C may diverge. This idea is straightforward to formalize in ROC, where the semantic signature of a statement C is a record. This record consists of 1 relation for normal termination and 2 subsets of program states for error and divergence. So, our first key insight is that we can describe the possible behaviors of a program using several simple sets. Then for each behavior set, we define an order or semantic operators to derive the semantics of program constructs. For instance, we formalize the behavior of sequential composition field by field. Normal termination is just relational composition. Errors and divergence are similar. For example, the sequential composition of C1 and C2 diverges if and only if C1 diverges or C1 terminates normally and then C2 diverges. We use the star operator and the infinity operator to derive the semantics of while loops. The star operator describes finitely many loop iterations, and the infinity operator describes infinitely many iterations of composition. Equivalently, normal termination is defined by taking a least fixed point, while divergence is defined by taking a greatest fixed point. In this way, we can build simple order rings and then take fixed points separately for each behavior set. To capture observable events from statements such as print, we can naturally enrich each behavior set with an event trace. More importantly, we distinguish finite divergence and infinite divergence. For finite divergence, the execution generates finitely many events and then silently diverges. For infinite divergence, there are infinitely many observable events as the program diverges. If we extend the composition operator by concatenating traces, we can apply the same method to define the semantics of program statements. This extended composition also keeps the same good algebraic laws as the original one. To handle the classic stuttering problem, we use two additional simple operators to describe the divergence of while loops. I will leave the details to our paper. Next, we extend the idea to procedure calls. We start again from a textbook setting. A program is a list of procedures. Each procedure consists of an identifier as its name and a statement as its body. To keep things simple, call statements have no arguments and no return values. Following the program structure, the semantics is defined step by step, first for statements, then for procedures, and finally for whole programs. First, the semantics of a statement is parameterized by an oracle chi. The oracle chi gives the denotations of callee procedures that the same may call. For the denotations of statements are previously introduced. The only new case is the call statement. Its semantics is defined directly by chi. Second, under the same oracle chi, the denotation of a single procedure or list procedures is a function that maps an identifier to a binary relation. For a single procedure, the binary relation is non-empty only when the input identifier is the same as the procedure's name. In that case, the binary relation is defined as the denotation of its body. For list procedures, the binary relation is defined as the union of the relations for each procedure in the list. Finally, the denotation of a whole program is defined by taking a list fixed point, which gives meaning to recursive calls between procedures. This is standard. Now we take error denotations and divergent denotations into account. So far, the oracle chi only describes normal termination, but how to capture errors and divergence from callee procedures. Our solution is to add a call behavior set. This set is a binary relation between initial states and queries at procedural call points. Here, a query records the identifier of the callee procedure and the state as a call point. For example, suppose a statement C may conditionally call F and then call G. Its call behavior set records all possible calls reachable from each initial states. As shown by the three legible arrows, when the if condition is true, C first calls F and then calls G. When the if condition is false, C directly calls G. The semantic signature of procedures has the corresponding fields. The difference is that a procedure starts from an incoming query. Similar to a textbook setting of procedural calls, the denotation of a single procedure is derived directly from its body. Finally, for a whole program P, the normal behavior is still defined by taking a least fixed point. Errors and divergence are then defined through a correlation. For example, divergence may come from local divergence or from an infinite chain of procedural calls. So we take the greatest fixed point of this semantic equation. This also explains why the call field is useful. The same idea extends to open modules. An open module is a module that may contain external calls. Its semantic definition is very similar to a previous definition for whole programs. The difference is that the recursive equations for internal calls are solved by a fixed point, while external calls are left open, and their meanings are given by chi-o. We can apply the same method to define the semantic linking of two open modules. Intuitively, Linking turns cross-module calls into internal calls. This gives us an equivalence theorem between semantic and syntactic linking. Here, the plus symbol denotes syntactic linking. It merges the procedural definitions of the two modules. We further found that this equivalence can be naturally reduced to the Beckett theorem. The diagram shows why this works for normal termination. Solving recursion inside M1 and M2 separately, and then solving their mutual recursion is equivalent to taking one joint fixed point after syntactic linking. Our second key insight is that this equivalence can also be extended to other behavior sets, such as error denotations and divergent denotations. The proof follows a simple algebraic pattern. Finally, let me turn to our proof method for compiler correctness. First, we consider simple transformations where the source and target use the same state representation. In this setting, transformation correctness can be defined by set inclusion. For deterministic but unsafe statement C, the target may have more normal behaviors. This is because once the source may go wrong, the compiler is allowed to produce any target behavior. For non-deterministic but safe statement C, the target may have fewer normal behaviors. This means that compilers may resolve non-deterministic choices in a particular way. But real program can be both non-deterministic and unsafe. In such more general cases, we describe transformation correctness as this. It means that every target normal behavior must either come from a source normal behavior or be justified by a source error behavior. For other behaviors, we define refinement in a similar way. This is where our separate behavior are useful. Normal termination errors and divergence can be compared precisely. Under this definition, the sequential compositionality follows directly. Let me briefly walk through a proof. One typical proof goal is to show that every target normal behavior is either a source normal behavior or be justified by source error behavior. The first proof step follows directly from the refinement assumptions for C1 and C2. The second step follows from the distributive law of composition over set union. The final step follows from the commutative and associative laws of set union. The final step is directly from the definition of sequential composition. This is exactly the proof pattern we want to preserve, since such proof can often be automated in ROC. For CompCert style transformations, set inclusion is no longer enough for defining transformation correctness. We need more general refinement relations because the source and targets may use different state representation. So similar to a simulation machine in CompCert, we define refinement between two denotations like this. For normal termination, this refinement condition says the following. Given a state matching relation R, for any related initial source and target state, every target normal behavior must either be matched by corresponding source normal behavior or be justified by source error behavior. The conditions for error and divergence are similar. To recover algebraic correctness proof, our key idea is to use the gamma function to reformulate each complex refinement as a simple set inclusion. Specifically, a gamma function takes source side behaviors and produces target side behaviors. Such a gamma is valid if and only if the reformulation has the same meaning as the original refinement condition. Our work shows that we can always find suitable gamma functions to reformulate each complex refinement as a simple set inclusion. More importantly, these gamma functions satisfy a common set of algebraic laws. With these laws, for example, the gamma normal is monotonic and preserves relational composition. This slide shows the general form of these algebraic laws. With these laws, even for CompCert style transformation, we can recover the same inclusion-based proof style we saw earlier. For example, consider the sequential compositionality again. A typical proof goal is to show that every target normal behavior is either a source normal behavior or be justified by source error behavior. The first step still follows from the refinement assumptions for C1 and C2. The second step is the key step. It follows from the composition preserved law of gamma. The final step is still follows from the definition of sequential composition. With gamma, the same algebraic proof style also scales to other cases, such as horizontal compositionality for separate combination. To conclude, these ideas give a denotational framework for compositional and structured compiler verification. We have applied our approach to the CompCert front end and also to optimizations such as data code elimination and constant propagation for simple imperative languages. That concludes my talk. Thank you.
Time for one or two questions.
Thank you for the excellent talk. I can't pretend to understand all of it. There's quite a lot there. I look forward to diving deeper. So with the refinement aspects of things, is it modeled as subset relations? And then I have a comment just generally that subset relations being logical implication. When you have a diamond, then you have non-determinacy. And if you think of modeling refinements as conjunctive sequences instead, you might be able to recover determinacy and scale.
So this problem seems to relative to our refinement conditions. Is that right? I mean, the problem is about the simulation relation about our refinement conditions. Is that right? I mean, you can. Our approach is to use a gamma function to reformulate the refinement conditions, complex refinement conditions. So you can recover the algebraic proof style for simple set inclusion. Even for complex refinements, we can use inclusion-based proof style to prove the compiler correctness. So.
Excellent. Maybe we take it offline. That's
okay.
Let's thank the speaker again.